Okay, here we are with electrons and atoms in the periodic table. Okay, we're going to start with electrons and atoms in section 5.1. Now, model the atom. Now, first of all, our objective for this part, okay, students are going to recall previous atomic models that we covered in chapters 4 and 25, and students will be able to explain the bright line spectrum of hydrogen, which is coming up. So, the concept of the atom has consistently changed with our discoveries over the past 200 years. We started with, in really revolutionary times, or just afterwards, where John Dalton came with the theory that atoms are unbreakable spheres. That every single element has its own. Every element has its own atom, and so the big concept here was the discovery of elements. Okay, and that elements have their own atoms. Now, later we discovered the nucleus of the atom, or we discovered electrons, and through using Thomson's plum pudding model, and that meant that these atoms had these smaller particles in them. They're called electrons, and they were embedded in a core of positive charge. And we knew that had to be positive charge because Dalton never mentioned anything about charge, and there was no reason to expect anything other than a neutral particle for an atom. And so if one part of it was going to be negative, the rest of it had to be positive to balance out the charge. Now, in 1911 then, Ernst Rutherford came up with his planetary model. And with his planetary model, he thought that there was this dense, hard center nucleus, and around the nucleus, electrons orbited in a circular path. And so you would have an atom here, and then around it, it would be traveling in a circle around the atom in a circular path. It had to be circular. Okay. And it had to be a circular path because the energy of the electrons, they had to stay a certain distance away from the nucleus. However, there was nothing keeping the electrons, because we knew they would eventually slow down. There was nothing keeping the electrons from falling into the nucleus. And so, we then had the Bohr model, which we will get to in a minute, where an electron can gain or lose energy by changing orbit. So they will go from their standard orbit, as shown by this model here, and they could jump out to an outer orbit, and then drop back, and then jump out, and then jump back. Okay, then 1926, we came up with the electron cloud model, and that electrons don't actually have a predictable path. They can exist in regions of probability space called orbitals. And this is a really obscure concept to grasp. And we'll try and get into more of that later and how we come up with these orbitals. But let's start with the Bohr model of the atom. Okay, the Bohr model was named for Niels Bohr, who was a Danish physicist. And his theory was that electrons orbit the nucleus in a circular path at different distances from the nucleus. Okay, so let's take our little drawing here and drag these guys down. Okay, and so the electrons would orbit in different distances from the nucleus, and the arrangement of those atoms determined what kind of atom it was and its ability to react. And his theory is based on the bright line spectrum of hydrogen, and we'll discuss that a little bit more in section 5 in 5.3 with spectroscopy and bright line spectrum. Electrons exist at the lowest possible energy positions with respect to the nucleus. This is called the ground state. Okay. and they make a quantum leap. Okay, so when electrons gain energy, they're sitting right here, okay, and they absorb a particular amount of energy, they will jump up to another orbit, which is some distance away. And this is an excited state, which means that they have gained potential energy. So think about it like this. Potential energy, I like to call potential energy cringe-worthy. Something is cringe-worthy. So imagine this: you take a brick, okay, and you hold it, a couple inches over somebody's foot, okay, and the person might start to feel a little bit uncomfortable about that, but they know if you drop the brick, it's not going to hurt a whole lot if it's just a little bit above the foot. Then you hold it above their head, and it's aimed right so that it will drop on their foot. Well, that has become more cringeworthy. The person's looking at you holding the brick, and you're kind of wincing a little bit, and trying to hold back from, you really don't want them to drop that brick on your foot. That is because the brick has gained potential energy. And potential energy is the ability to do work. It has the ability to send its energy somewhere else. So electrons, when they jump out to a higher energy level, they reach what's called an excited state, and they have increased their potential energy because they're further away from the place that they want to dive into, which is the positively charged nucleus. Now, when these excited electrons lose their energy from a quantum leap, they return to their lowest energy state and release this energy in the form of electromagnetic radiation. Okay, and in some cases, this electromagnetic radiation is visible light. The light that we see is actually radiation, electromagnetic radiation, and our eyes pick it up. Okay, this produces what's called the barcode of the element, known as the bright line spectrum. Now, the problem here is the math that they do to figure out the energy levels and how much energy the electron gains by jumping up to a level, and then how much it releases by jumping down to another level. The math only works for the hydrogen atom. Okay, and why is hydrogen different from all of the other atoms? It only has one electron, which makes things very simple for the hydrogen, because it just jumps out and it jumps back, and that one electron is easy to track based on the energy that the atom absorbs. When you have multiple electrons in there, there are multiple combinations of energies that these electrons can absorb, and so it is much more difficult to track. Okay, so I'm going to pause here, or you should pause here, and you should be writing your notes on the side of the page. So we're going to hit pause. Okay, so you're going to hit pause, and I'll cover the screen to remind you to do that. Grab it. And you go ahead and write your notes for your lecture. And we're back. Okay. So, the next objective, the objective for this next section of lecture is I want you guys to demonstrate the understanding of principal energy levels, sublevels, and orbitals. Okay, so this brings us to the quantum mechanical model of the atom. Okay, it has the same components as the Bohr model. However, it describes the nature of electrons differently. Electrons cannot orbit the nucleus in definite circular paths because of the repulsion and attraction. Electrons are repelled from each other, and they're attracted to the nucleus. And so it'll never, ever work in a perfectly circular path. There's always in and outs and that sort of thing. And we've also discovered that electrons act as waves. Okay? And part of the wave pattern is this orbital. Now, electrons do not orbit the nucleus as stated by Bohr. They are found in regions of probability space called orbitals, which are found in energy levels. Okay. Now, orbitals are regions of space with a definite shape, size, and energy, but they don't really describe how electrons move. Okay, and they move in these things called electron clouds. And those are the regions of high probability space. They are high probability regions of space that determine the size and shape of the orbital. I like to compare this to a darkened room with a single light bulb that is filled with moths. The moths are going to be flying all over the place, and you can't really track any one of them and where they're going to go. But you know that they're all going to be close to the light, and they're going to be zooming past the light bulb and then flying away and zooming past and then flying away. And most of them are going to be around the light bulb, with a few of them further away, because the moths don't particularly like to be around each other. They get in each other's way when they're flying. So if you can imagine, you take a sphere, take a giant sphere around the light bulb, and you could imagine that there would be a sphere that would hold 90% of the moths around that light. Okay, because it'd be pretty much everywhere, above and below, and so there would be a region of space that would hold, say, 90% of the moths. That is a region of probability space. That if you picked any particular moth, there would be a 90% chance that you would find it within that region of space. Okay, classrooms are high probability regions of space. Okay, at 90% of the day, you choose any one particular student, and the chances are that they're going to be in a classroom during the school day. Okay, so classrooms are regions of high probability space. They're physically bordered by walls, but you'll probably find a student in one of those classrooms during the day. Okay, which brings us to principal energy levels. And when electrons are in orbitals, they have principal energy levels. Or electron shells is what you might remember calling them from your biology class. And each energy level is limited to certain numbers of electrons. Okay? They are layers of electrons surrounding the nucleus. Now, the first energy level is the lowest in the potential energy, followed by the second, followed by the third. So the further away you get, the more energy that the level holds. Now, energy levels have letter designations starting with 1, and then 2, and then 3, and then 4, and so on. Okay, all the way up to 7, okay, which it does go up there. Okay, and they have letters, but you don't have to know the letters. Okay, the maximum number of electrons possible in any principal energy level is determined by the formula 2n squared, where n equals the energy level. So if in the first energy level, 2 times 1 squared equals 2 electrons. At the second energy level, 2 times 2 squared is heat, electrons. Okay, then if n equals 3, you'll get 2 times 3 to the n, to the second power, is 18 electrons. And some of you might remember from biology, your basic biology chemistry, the orbitals, the 2, and then 8, and then 18, and 32, and so on. Okay, and so I repeat myself a little bit here. Okay, and so, for example, energy levels 2 and 4, at the second energy level, we get 2 times 2 electrons squared, which is going to be 8 electrons maximum at level 2. And if we do the 4, then it's going to be 2 times 4 squared, which would be 16. I'm sorry, 32. 2 times 16 is 32. Okay, so we're going to pause here for a second, and I'm going to throw up the revealer again, and I want you guys to summarize everything you had right there. Okay, and here we go. Now, then we have sublevels, because electrons can't just be, they have to be more organized than just overall energy levels. Okay, and so we're going to learn what the S, P, D, and F stand for in the quantum mechanical model. Now, all principal energy levels contain one or more sublevels where electrons exist. These sublevels are named by the lowercase letters S, P, D, and F. I have no idea where these letters come from. I imagine there's some sort of German thing because it was German physicists that figured this stuff out. But I've never learned why they're named S, P, D, and F, and you don't have to know either. Okay. C. Each principal energy level has the same number of sublevels as the level number. So the first energy level is going to have one sublevel. The first time we see the S sublevel is in the first energy level. Okay. Then energy level 2 has two sublevels, S and P, and the first time we see P is in the second energy level. The third one has S, P, and D, and the first time we see D is in the third energy level. The fourth one has S, P, D, and F, and the first time we see F is in the fourth energy level. And it keeps going on. It actually goes F and then G and H and I and so on. Although I don't know if there's I. Might be J. However, those are very high energy, and we don't have any atoms that actually hold electrons in those outer energy levels, in the G and the H and the I, that occur in nature. They'll get up to F, but that's about it. Now, within each sublevel, there are regions of space where electrons exist most of the time. These regions are called orbitals, okay? And these orbitals are the regions of space where electrons reside. So, pause there, and let's summarize that section right there. 7. Okay, pause. And we go. Okay, now, these orbitals have names that explain their position inside the sublevel. Okay? For example, okay, the P sublevel has 3 orbitals, and there are 3 orientations. And these are actually pretty cool looking. Okay, and so our p orbitals, our orbitals have names that explain their position themselves. For example, our p sublevel has 3 orbital orientations. So I'm going to show you those here in a second. Okay? Those look like this. Okay, this is the s orbital. It's only got 2 electrons in it. Okay, it is the most basic one, and it is just a sphere. S is for sphere. P, I have no idea what P is for, so S isn't necessarily for sphere. I'm just saying it might be for sphere. Okay, now the P has 3 different orientations, and they look like these dumbbells. And see how one is along the x-axis, and one is along the y-axis, and one is along the z-axis. And those are 3 different orientations for the S and P orbitals. Okay, and so there's 3 orientations for it. Okay? And each orbital shape has its own set region of space, where the one is orbital, the first orbital is spherical. The P sublevel, each one is bilobed, or dumbbell. We'll call it a dumbbell. Okay, this is not an insult for anybody. It is just what these things are called. Okay. Then the D level has 5 orbitals, and it's even more complex, and it has 5 different orientations. And it looks like this. Okay. The D orbitals look like this, where you have these 8 lobes to them. And notice how they're in between the axes, how this is flat in the XY plane, but the lobes are in between the X and Y axes. And this one is flat in the XZ plane, and the lobes are in between the X and Z axes. And same thing with this one is in the XY. And then this one is on, well, check this one out. This one is on the XY axis, and this one is on the Z axis, and it's got this little loopy thing right here. Okay, and this is going to relate to the spring demonstration we're going to do in class, where S's have a spring that looks like this, and then it loops like that, and the P's are going to have a spring that looks like this, And then the D's are going to have a spring that looks like that. And you can kind of see that how this would be, this right here would match this loop. And this right here would match this loop. And this one is kind of looping around. Okay, maybe that's a tough sell. Okay, but those are the orientations and those are the sublevels that we're looking at. Now, only 2 electrons can inhabit each orbital. Okay, regardless of the type of sublevel. So, okay, so in the s sublevel, there's going to be 2 electrons total, 1 orbital times 2 electrons. In the p sublevel, there's going to be 6 electrons total, which would be 2 electrons and 2 electrons and 2 electrons. Okay, so this is going to have 2 electrons only. This is going to have 2 electrons and 2 electrons and 2 electrons all together for this p orbital. Okay, d sublevels are going to have 10 electrons because it's going to have 2 electrons and 2 electrons and 2 electrons and 2 electrons and 2 electrons. So that's a total of 10 for the whole d sublevel. And finally, we have the f sublevel, which I do not have a picture of, I don't think. Okay, and f sublevels, they're crazy. So imagine taking a D, okay, and have a loop go out, and a loop come out, and a loop go out, and a loop go out, and then do the same thing down low again. Okay, so you have 4 loops coming up and 4 loops going down. It kind of looks like mitosis. I don't remember what phase it is, but it looks like a phase of mitosis. Okay, which brings us to spin, and electrons spin on their axis, and there's a couple of reasons behind it. Because we have to maintain angular momentum, which is how they have to spin a certain direction. And electrons in the same orbital can't have the same spin, or else they might actually become each other, which is a really weird quantum mechanical thing. But electrons spin on their axis, and it creates a tiny magnetic field. And that magnetic field only allows for an electron of the opposite spin to come in. And so it's like a North Pole, South Pole kind of thing within any particular orbital. And so only electrons of opposite spin can stay in the same orbital. Okay, that is the end of 5.1. So we're going to stop there and make sure you summarize your notes for this particular lecture. And I believe I'm going to assign you guys your homework now. Okay, so your homework is going to be section review 5.1 and these problems right here. So go ahead and knock those out for tonight, and we'll see you, or this is what you're going to be working on tomorrow in class, or we're going to work on that right now, however we decide to work on it. Okay?